Today we're going to start a new unit. This is sometimes what I call our hump unit, in that we're now going over the hump into the second part of the second half of the year. We've got kinematics, which we've covered. We've got dynamics, which we've covered. We've still got some stuff on waves left, but we've also got, and we've got this circular motion stuff left. Okay, this is the point where we cross that border between approaching the halfway point and going past the halfway point. Okay, so it's not like we're on the home stretch yet, okay, but we're at that point where we're kind of in the second half of what we do. The unit is called uniform circular motion, and what that means is, I think part of this is pretty clear and pretty obvious what it means. Circular motion means object moving in a circle, right? Uniform circular motion means object moving in a circle at a constant speed. So we're going to be looking at situations, not all situations in which an object is moving in a circle. We're looking at situations in which the object is moving in a circle, but moving at a very specific speed. So not speeding up, not slowing down, moving at a constant speed. Let me just define that for you right now before we go any further. Let's say motion of an object in a circle moving at a constant speed. I understand that there are situations in the real world where things are speeding up while they're moving in a circle or slowing down while they're moving in a circle. But there's also a lot of situations where they're not, where they're moving at a constant speed. And even some of the ones that are speeding up or slowing down while moving in a circle can still be reasonably approximated by uniform circular motion, or reasonably approximated by looking at the object as if it was moving at a constant speed. I'll tell you, when we encounter something, I'll tell you if it's reasonable to approximate whether it's going at a constant speed or not, whether we can use uniform circular motion principles to solve these problems. Okay? Largely the roller coaster problems that we're going to be doing next week when we go on our field trip, they can be approximated by uniform circular motion principles. Okay? Sometimes the roller coaster cart is speeding up a little bit, or it is slowing down a little bit, but it can be considered to be moving at a constant speed because it's a good approximation. Again, I'll tell you when you can and when you can't. Three terms that we've got to go with here now before we look at this any deeper, though. Two of them are new. Frequency and period, brand new terms. The last one, speed, you've seen that a million times before, but we'll talk about it in the context of circular motion here. Frequency, if you think about when you've heard that word before, frequency. Frequency means how often something happens, right? How often something happens, how much something happens, the rate at which something happens. Well, when we're talking about circular motion, that's something, the event is the object going in a circle. The roller coaster cart going around the circle once, or the car going around the racetrack once, or as I swing my keys, the keys going around my head once. The event is the object going in the circle. So how often that event occurs is essentially how many revolutions of that circle we have per unit time. So that's the way we're going to define frequency, is the number of revolutions per second. It could actually be defined as the number of revolutions per minute, or per hour, or per day, or per year, but the standard unit that we use is seconds, so that's what we'll go with in our definition. You may see frequency expressed in revolutions per minute. You want to find the number of revolutions in a second, all you do is divide that number by 60, because there's 60 seconds in a minute. The number of revolutions per unit time, or the number of revolutions per second. The symbol for frequency is a lowercase f. And if we want to write an equation that relates to the definition that we just gave, it would be the number of revolutions divided by the time. The units that we would use to describe frequency would be revolutions per second. Or there's another unit that we can abbreviate this with, that we can kind of shorten it up with a bit. Instead of calling it a revolution per second, we can call it a, you've heard this unit before, although you may not know what I'm talking about here right now. We haven't seen it in physics. You've probably seen it somewhere else. Anybody know what it is? Well, RPM, yeah, RPM, but be careful because RPM means revolutions per minute as opposed to revolutions per second. So the equivalent to that would be RPS, although you don't see that one nearly as often as RPM, right? Okay. RPS, we could say. Any others? Boy, it hurts me that you guys can't think of this. It really hurts me. It really hurts me that you can't come up with this one. What is it, Brian? Hertz. So 1 revolution per second is 1 hertz. If you talk about revolutions per minute, okay, then obviously you get more revolutions per minute than you would get per second. So the number of revolutions per minute would be a bigger number than the number of hertz. All you'd have to do, though, convert it pretty easily. Just divide by 60 to get hertz, or revolutions per second. Period. Period's similar to frequency, but it doesn't mean exactly the same thing. In fact, it's the inverse of frequency, but it's clearly related to it. If frequency is the number of revolutions per second, then period is the time per revolution. Instead of how many revolutions are taking place in a certain amount of time, it's how long it takes for a revolution. The time per revolution. And the symbol for period is a capital T, big T. Now, don't make the mistake of calling it a lowercase t. Don't make the mistake when we're looking at just regular time like we have up until now of calling it a capital T. Lowercase t and capital T from here on out mean 2 different things. Lowercase t means just any time, okay, just a general time. Big T means very specifically the time for 1 revolution. Now, how are we going to find that? Want to find the time for 1 revolution? Let's say it's the time divided by the number of revolutions. It's the exact opposite of frequency, right? The inverse of frequency. Now, the units for that would be, well, we could say it's seconds per revolution. Sometimes we actually just say it's seconds. We drop the revolutions on the bottom and just say seconds. And there is no abbreviated thing like hertz for the period. The good news is neither of these are that difficult. The bad news is neither of these equations appear on your data sheet. The following equation does appear on your data sheet, though. T is equal to 1 over F. Where does that come from? Well, if frequency is number over time, and in period is time over number, then the period is the inverse of the frequency. So period will be 1 over F, or F would be 1 over T. So this one does appear on your data sheet, although you do have to be familiar with these as well. The reason that these don't appear on your data sheet is because they're not so much equations, they're more definitions than equations. Speed. Well, we're talking about uniform circular motion. So we're talking about objects moving at a constant speed as they go around the circle. Right, Alana? Can you put it away, please? So we're going to use the equation V equals d over t to describe that. But we're going to change this equation around a little bit, derive a new equation from this equation. What's the distance around the circle called? The distance once around the circle. What's it called? Aiden, you know it? Good, it's the circumference. Does anybody know the equation for the circumference of a circle? Carrie? No, be careful with that. Tyler? 2 pi. Oh, you're both close. Let's go in between. You said 2 pi. You said 2 pi r squared. Let's go in between 2 pi and 2 pi r squared. Let's call it 2 pi r. Sometimes people call it pi times d, pi times the diameter, or 2 times pi times the radius. Carrie, how do you keep straight pi r squared and 2 pi r? And I'll tell you, when I was your age, I always used to get those mixed up. Okay, pi r squared is the area of a circle. 2 pi r is the circumference of a circle. But I'm no different than you. I got them mixed up all the time when I was your age. So how did, in the end, I end up keeping them straight? How do I now remember that circumference is 2 pi r and never forget that? Well, look at the units. 2 pi r gives me meters. Pi r squared gives me meters squared. Which one's going to be circumference, meters or meters squared? Got to be meters, right? Meters squared gives me area. So even if I forget what the equation for circumference is, I stop and I think, okay, what are the units for this equation? And does it make sense that that would be for circumference? In this case, it does, right? Because the units are meters. Pi r squared, the units are meters squared. It doesn't make any sense for circumference. Okay, it works for area. Okay, so that's the distance around the circle one time, the circumference, 2 pi r. If we're using the distance around the circle one time, then we have to use the time around the circle one time. What's the time around the circle once called? How long does it take to go around the circle? There's a term that we've already defined that means the time around the circle one time. The period. So instead of saying v equals d over t for the object moving in a circle, we're going to say v is equal to 2 pi r over t. That equation is also on your data sheet. Every time an object is moving in uniform circular motion, which it will be for us in this unit every time, we'll say v is equal to 2 pi r over t. So far, so good? Well, this unit is easy, isn't it? Let's take a look at a problem here. There's a diagram that goes with this, but we don't really need the diagram. The hard drive, which is the part in a computer, in most computers, that stores not the workable memory of your computer. It's called the RAM, random access memory, that uses that, you know, as you're doing things on your computer, the processing that takes place and the things that are stored in this thing called RAM. But the hard drive stores data that you're keeping, right? When you save a file, it's on a hard drive, in most computers at least. In some computers, it's use what we call a solid state drive, but most computers, it's still a hard drive. Hard drives physically use this device that spins around. It's kind of like a CD that spins around, except it doesn't store the information optically like a CD. It stores the information magnetically. Okay, but it spins around just like a CD spins around. On a thin magnetic platter that's spinning at a high speed, if it makes one complete revolution in 0.00833 seconds, which, by the way, is a pretty realistic number, but kind of amazing when you think about it, right? This hard drive is spinning around, and it makes a whole revolution in 8/1000ths of a second. Yeah, that's how fast it spins. It's got to spin that fast. If you want to have reasonably prompt access to your data, it's got to be spinning around fast, because if it's spinning around a lot slower, it's going to take a lot longer to access your data and to access your programs. So it's got to spin that fast. Sometimes they spin even faster than that, but this is pretty typical though. We want to find its frequency in hertz and in RPMs. RPMs, Jacob, stand for what? Good. So if we find it in hertz, then all we have to do is multiply it by 60 to get revolutions per minute, right? That's the easy part of it, right? The hard part of it is the first part, getting the frequency in hertz. Okay, what do we have given to us? Something is 0.00833 seconds. What is that? What variable is it? It's a time, right? But what time is it? Is it T, T1, TI, TF? What is it? Good, it's big T. Okay, it's the period, the time for one revolution, big T. We want to find frequency. That's going to be little f. Don't call it big F, right? It gets confusing now. We used to call it little t, now we're calling it big T. We used to have big F for force, now we got little f for frequency. The reason that it's not force or frequency is not capitalized is because we don't want to get it mixed up with force. The reason that period is capitalized is because we don't want to get it mixed up with just any other time. How am I going to find frequency here? We know that frequency is the number of revolutions per second, but we also know that it's 1 over t. What do you want to use here to find frequency? Yep. Good. Let's try F is equal to 1 over T. 1 over 0.00833 seconds. This doesn't look that hard. Let's pull out our calculator and do this. Here's a little trick on your calculator. I don't know if you guys knew this or not. You can go 1 over 0.0083, press equals, or you can just say 0.0083. Anybody ever use this button here, x to the minus 1? That means 1 over. So we get the exact same thing, right? So if you ever have to flip something over, take the inverse of something, you can just type in that number and go x to the minus 1, and it'll give you the answer there. 120.4819. And that's going to be in hertz. 120 hertz, rounded to 3 digits. Now we want to find the number of revolutions per minute. Jacob, again, what do we do? Sorry? Divide by 60? Let's think about that, guys. Jacob, I'll tell you what. When I was in grade 8, still, I make that mistake sometimes. Do I multiply or do I divide? Even 42 years old, 20 years after I graduated from university, I'm still making that mistake sometimes about whether I multiply or divide. Here's what I do sometimes. I guess. Sometimes. But then I always check my guess. So Jacob, let's say we guess we're dividing by 60. Okay, 120 divided by 60 gives me 2, right? If I have 120 revolutions in 1 second, am I going to have 2 revolutions in a minute? No. So that's okay to guess. Just check your guess to see if it makes sense. In this case, it doesn't. So if it's not divide by 60, it must be multiply by 60. Good. We're all going to make those mistakes. The key is catching those mistakes. So let's take 120.4819 hertz. That's revolutions per second. Multiply by 60, because there's 60 seconds in a minute. And that gives us, I think it's 7,200. 7.20 times 10 to the 3 revolutions per minute. 7,200 times every minute this hard drive spins around. You can start understanding here now why hard drives sometimes crash. They're going for hours upon hours upon hours a day, and they're spinning around 7,200 times every minute. At some point, something is bound to happen to it, right? Something's bound to go wrong if it's spinning around that much, okay, and it's on for 12 or 15 hours a day. Is that a hard question? Good. We're well on our way then. Let's take a look at these 3 questions. We'll give you just a few minutes to do those, and then we'll push forward from that. Any issues with any of those 3 questions, guys? Yep, absolutely. Number 3 it is. It says a medical centrifuge is a device that separates blood into its parts. A centrifuge is actually a thing that spins really, really fast. You guys know from sometimes amusement park rides, there's one at Callaway Park. I can't remember what it's called, but it's you get in this this outdoor, it's green, I think, metal thing. It spins around and you get pinned against the wall. Hey, they have one at the Stampede sometimes called the Gravitron. It's similar to that, except it's inside. You can't see outside. Okay, those are both centrifuges. Centrifuges work by spinning, and they use the principle of inertia. You want to go in a straight line. As you're spinning around, you want to go in a straight line. So you're right here. You want to go in a straight line. Well, what ends up happening is you end up being pushed out to the side because you want to go in a straight line. Well, blood centrifuges do exactly the same thing. They separate the blood into its parts by pushing them to the outside by inertia. I say pushing loosely, use that term loosely, because it's not really pushing. Okay, it's inertia that wants to take them to the outside, take them in a straight line. But the parts of the blood that are heavier want to go out more because they have more inertia, right? Inertia is dependent upon mass. Heavier things have more inertia. They go to the outside quicker. So we can separate blood into its components simply by spinning it around really, really quickly. The heavier things will go to the outside. The lighter things won't go to the outside quite as much. Does that make sense? We also, or not we, but countries, scientists can also use centrifuges to separate uranium. Okay. Why would they want to separate uranium? Now, because in order to build a bomb, a nuclear bomb, you need what's called enriched uranium. And normal uranium is about 97 or 98% unenriched. In other words, it's one isotope of uranium. We want a higher purity of uranium-235. So what do? We spin it around, and the heavier stuff goes to the outside. The lighter stuff doesn't go to the outside quite as much. So we split up this uranium by the centrifuge, the same way as we split up blood. It's a little bit harder to do than it is for blood, okay, but same basic principle. Anyways, the centrifuge can spin at 6 times 10 to the 4, 60,000 revolutions per minute. We're going to circle that revolutions per minute because we know that we want hertz, and that's not hertz. We want to find the frequency in hertz, and we want to find the period. We know the frequency here is 60,000 revolutions per minute. We want revolutions per second. Jacob, how are we going to find that? Good. We're going to divide by 60. Okay, if we multiply that by 60, we'd end up with a number that's way bigger than that. Well, you're not going to get more revolutions per second than you get per minute. So it's got to be divided by 60. So let's do that. Let's divide it by 60. We're still going to get a frequency, but this time the frequency is going to be in revolutions per second, or hertz. Works out to be 1.0 times 10 to the 3 RPS, or 1.0 times 10 to the 3 hertz. Question? Yes. Yes. No, sorry if you... hold on for a sec. Yes. Yes. No, you're right. Yeah, absolutely. Yeah, I just had to think about that for a second, see if it made sense, but it does. Now, if you times it by 60 again, we're saying here that we get revolutions per hours, right? Which, not a real common unit of frequency, but just as valid as revolutions per minute, just not quite as common, that's all. You times it by 24 revolutions per day. Times it by 365 revolutions per year, right? All right, now we want to find the period. Haley, how am I going to find the period? Yeah, 1 over the hertz, 1 over the frequency. So 1 over 1,000, which is 1.0 times 10 to the negative 3. And the units of that would be seconds. Right? Here's another one to try. This one says a pebble was stuck in the treads of a tire at a distance of 36 centimeters from the axle. There's a picture there, but you know what? We could draw our own picture. Okay, here's the axle. Okay, this is the middle around which the wheel spins. And this is the edge of the wheel where the treads are. There's a pebble stuck in the treads of the wheel at the edge. We know the distance from the axle is 36 centimeters. So let's fill that in right here at 36.0 centimeters, which we want to be careful because in the end we're going to want meters for this, right? So it'd be 0.36 meters. Takes 0.4 seconds for the wheel to make 1 revolution. What is this 0.440 seconds correspond to? Yep. It's going to be the period, the time for 1 revolution, right? Period. We want to find the speed of the pebble at any instant. How fast is the pebble moving? Well, V is equal to 2 pi r over t. 2 times pi times 36.0. Let's convert that to meters. 0.360 meters divided by the period, 0.40 seconds. So it's going to be 2 times pi, second function, button right there, times 0.36. Let's divide that by 0.4. Get 5.65 meters per second. Is that right? 5.65? 30 centimeters? No. Is that right? 5.6548 meters per second. Where should I round that to? Where should I round that to? 1 digit, 2 digits, 3 digits, 4 digits? What should it be rounded to? 2 digits, right? As you go back to this one, this is 3, this one's 2. Final answer should be 2. 5.7 meters per second. What happens if you've got a car and you decide, I don't like the size of the wheels on this car, I'm going to change it. I'm going to put bigger wheels on the car, or I'm going to put smaller wheels on the car. What happens? Yep. Well, no, the revolutions per second would still be the same because that's based on essentially your transmission, right? Your engine and your transmission. But the radius is different, right? So the period is the same, the radius is different. If you increase the radius, in other words, you go with bigger wheels, then what's that going to do to the speed that your speedometer measures? If you have a bigger radius, you're not going faster. Sorry, if you have a bigger radius of wheel in the same amount of time, it's going to measure it as going faster. Right, Gary? Yeah, it does because it's a principle called torque actually there. It's rotation from the pivot point, so it needs more torque. It needs more torque to turn it. But what it does is ends up essentially messing up your speed, right? So in the end, the speed that you measure with your speedometer isn't necessarily the speed that you're actually going. Does that make sense? You measure a speed with your speedometer, but wait a second. That's based on a certain size tire. So all of a sudden, if you change your wheels, I shouldn't say a certain size tire, a certain size wheel. If you've got 15-inch wheels and you put 16-inch wheels in, then all of a sudden, the distance that wheel covers in one revolution is different. Your speedometer measures how many revolutions your wheel makes, basically. So if it makes the number of revolutions that the speedometer expects, but the distance covered during that time is different, then your speedometer is going to be off. So you end up with a speeding ticket because you have different size wheels. All right, try these ones, guys. 1 and 2 on 251. Let's have a look at question number 2 here, everyone. Number 2 says, in 2006, an Alberta astronomer discovered the fastest spinning collapsed star, which is called a pulsar, spinning really, really, really fast, ever found. It has a radius of only 16.1 kilometers. So we're going to say R is 16.1. We could say 16.1 times 10 to the 3 meters, or we could say 1.61 times 10 to the 4 meters. Doesn't really matter. Okay, for me, a little bit easier just to say, look, I'll tack on a 10 to the 3 on the end of it, because that's what a kilo is, 10 to the 3, right? Spinning at a rate of 716 hertz, that's going to be the frequency, right? We want to find the speed of this thing at its equator, right? How fast is it moving at its equator? If you're standing on this thing, on the equator, how fast are you moving? Well, we know that V is equal to 2 pi R over T. So it's 2 times pi times 16.1 times 10 to the 3 divided by T. What's T? We don't know what T is, right? Any ideas? Any ideas there, Jacob? Good. T is equal to 1 over F. Both of these equations are on our data sheet. So T is equal to 1 over 716. And Jacob, what do you get for that when you divide those two numbers? 00139. Okay. Oops. Oh, this isn't aligned quite right. 1397. So let's put that number in here, 0.00137 seconds. Calculate the speed, and I think we should end up with 7.24 times 10 to the 7. 724 something, 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 something. I had a person ask me, well, how do we put that in scientific notation? Because really it needs to be in scientific notation so we can have 3 digits, right? Let's do this on a calculator. I'm going to show you a little trick if you have trouble at all with put it in scientific notation yourself. So we're going to say 2 times pi times r, which is 16.1 times 10 to the 3. I'm going to divide that by 0.001397. Okay, that's my number. Okay, some of you are good at putting that in scientific notation already. Okay, all you have to do is count the decimal places, right? 1, 2, 3, 4, 5, 6, 7. 7.24 times 10 to the 7. But if you have trouble with that, for whatever reason, or you just don't feel like doing it, let me show you a little trick. Right now, your calculator is in degree mode. It's in standard notation mode. Okay, if I multiply that number by 1, then I end up with the same number. But if I do this, hit the mode button, and then scroll over here to scientific notation instead of normal notation, and then I multiply that number by 1, look what I get. 7.24 times 10 to the 7. So if you don't feel like doing the counting yourself, or you think you might make a mistake with that, then just put it in scientific notation right on your calculator. Okay, and it'll spit it out for you. Right? Good? Good. What I'm about to talk about right now for the next couple of minutes before the end of class here may not make sense to you if you're thinking. Ironically, if you're thinking, it may not make sense. If you're not thinking, if you're just kind of accepting what I tell you, then it makes perfect sense. We're going to talk about what we call centripetal acceleration and force. Let's look at the acceleration term first. Explain this to me, please. If an object is moving in a circle at a constant speed, because that's what uniform circular motion is, how can there be an acceleration of any type? Keys swinging around my head right now, constant speed. Oops, I almost let those go. Leah, you are almost maimed there. Got him now. You're safe now, Leah. Swing these around my head, moving at a constant speed. How is there an acceleration if they're not changing speed? But why? Okay, you're right. In the end, you're right. There is an acceleration toward the center. But how? Why is there an acceleration toward the center or in any direction if it's not changing speed? Don't we have to speed up or slow down to accelerate? Yeah. What do we define acceleration as? The rate of change of what? Good. It's not the rate of change of speed. It's the rate of change of velocity. As I swing these keys around my head, is the speed changing? No. Is the velocity changing? Yes, because velocity has a direction, and the direction is changing. So you understand, as you move in a circle, the direction is always changing. Therefore, even if you are going at a constant speed, the velocity is also always changing. And if the velocity is changing, then you've got an acceleration. Somebody said, Aiden, was it you that said it's accelerating toward the center? Okay, Lewis said it was accelerating toward the center. We'll worry about that later on. Okay, right now, just recognize that there has to be an acceleration somehow, some way, if it's changing velocity, and it is changing velocity as long as it's changing direction. And of course, if you have an acceleration, then you've also got a force, right? Call it a centripetal acceleration and a centripetal force. But again, we'll get into more detail about why that's called centripetal and why it's toward the center in just a little bit here. The centripetal acceleration is the acceleration of an object moving in a circle directed toward the center. So the acceleration, just as Lewis said, is directed toward the center. I'll explain why in a minute. Whereas the centripetal force is, if there's an acceleration directed toward the center, then there has to be a force directed toward the center as well. The force acting on an object moving in a circle, the force that's directed toward the center of the circle. As I swing my keys around my head right now, they're moving in a circle. Which way do they want to go? Just stop writing for a second. Which way do my keys want to go? Yep, in a straight line. But they're not going in a straight line. Why not? Well, something's keeping them from going in a straight line. It's a force. We call it a centripetal force. What's applying the centripetal force? What is it exactly that's keeping these keys from going in a straight line? Yep. My hand. Right, good. My wrist, my hand is keeping these keys from going in a straight line. Where is my hand? Stephanie, where's my hand? In the middle, right? So if the force that's being applied to keep it from going in a straight line is supplied by my hand, which is in the center of the circle, then the force must be directed toward the center of the circle. And if the force is directed toward the center, then the acceleration must be as well. The centripetal acceleration is the acceleration directed toward the center. The centripetal force is the force that's directed toward the center. Two more equations here now. Centripetal acceleration, we're only going to find the magnitude of it. We don't need to find the direction with the equation because we know the direction. It's toward the center of the circle. The centripetal acceleration is v squared over r. What does v stand for? Yep. Speed, not velocity, because the velocity changes. Speed's not changing here. R stands for what? Yep. Good. It's the radius of the circle. What would the units for centripetal acceleration be? That's an easy question. What are the units for centripetal acceleration? Okay, if you think you know the answer, then you probably do. Okay? Meters per second squared. Good. Same as any other acceleration, right? What about centripetal force? Well, force is m times a. What's a? Yep. V squared over r. So the centripetal force will be m times v squared over r. What would the units for centripetal force be? Another easy question. If you think you know the answer, then you probably do. I shouldn't preface a question with easy. Because sometimes, we make a little mistake. It's not sometimes easy, but Lewis, what is it in this case? Newtons. And of course, if force is measured in newtons, any force is measured in newtons, so is centripetal force. Understand this, okay? Centripetal force is not what we consider to be a fundamental force. It's always caused by something else. It's essentially taking another force and renaming it. When I swing my keys around my head, there's the force in my wrist that's pulling it toward the center. Well, let's rename that the centripetal force. When a roller coaster goes around a loop, it's really the force of the track that keeps it from going in a straight line, right? Let's rename that the centripetal force. When the car goes around a turn, what keeps the car going around the turn in a circle as opposed to going in a straight line? Yep. The tires, and therefore the force of friction. The force of friction. Well, let's rename the force of friction the centripetal force because of the direction that it's pointing. As the Earth goes around the sun, what keeps the Earth in orbit around the sun? In more or less a circle. Not quite, but more or less a circle. Gravity. Right? Well, let's rename gravity the centripetal force in that case because it's pointing toward the center of a circle. Does that make sense? This mv squared over r force is never a force that stands on its own, ever. It's always caused by gravity or friction or my hand or by something. It's always caused by something. Got it? The motion of an object at any point is a straight line. We call that a tangent to the circle. We do a tangent line back when we were finding instantaneous velocity back in Unit 1. Right? Tangent to the circle is just a line that kind of skips off. So if we have an object moving counterclockwise here, then the velocity at this point would be this way. The velocity at this point would be this way. This point would be this way. Always drawn at a tangent to the circle. V would represent velocity. Whereas green would be what? If red is the velocity, then the green arrows represent what? Anna? Away. Yep. Nope. Don't make this harder than it has to be. Nope.
Get one more in Mr. Coder's room, please.
The centripetal force. It could also represent the centripetal acceleration, right? Because both of them point toward the center of the circle. Good? We'll wrap it up there for today, guys. We'll pick this up tomorrow at this point. All right, that's it for tonight. Have a good day.